Okay, so now some of you are probably wondering what the first video really had to do with the limit. We never said the word limit, right? All we were really doing is to try to figure out what's going on around x equals 0 for that specific function. We took values that were very, very close to 0, plugged them into the function, and saw what we got, right? We looked at what we got when we plugged those things in, and we saw that those output values that we were getting were very, very close to 1. And so we had an idea that the behavior around x equals 0 was that the function was approaching 1. Okay, so now let's formally define what a limit is. So if the values of f of x can be made as close as we like to some finite number L as x approaches the value of c, then we say that the limit of f of x as x approaches c is L, and we write this specific notation here. So you see like lim, and then right below it, x with the arrow c, and then of f of x equals L. Okay, and here I'm just saying otherwise we say the limit of f of x as x approaches c does not exist. So if it doesn't approach a specific number, a finite value L, then we would say that the limit does not exist. But we'll talk more about that on another time. Okay, so I know that's a lot of very complicated words, but let's talk about more informally what this means. What it really means is the limit just tells us the output value the function f is approaching as the input value, in this case x, approaches some value c. Okay, and so what I'm saying here is in the example above, we would use the following limit notation. And what we would say is, as x approaches 0 of the function sine of x over x, we would say that the limit as x approaches 0 of sine of x over x is equal to 1. Okay, so instead of writing what we wrote up here as x approaches 0, f of x approaches 1, we would just say the limit as x approaches 0 of our function f of x is equal to 1. Okay, so it's very similar but not quite as far as the notation goes. But all it's really telling us, all the limit is telling us, is what output value we're approaching as our input value approaches a specific value. Okay. So now some of you might be wondering, why do we even care about limits? And other than the fact that I think they're beautiful, this tells us more information about the behavior close to a point. And this is specifically helpful if the function is undefined. So in our example in the first video, you saw that if we wanted to know the function value at 0, we would have just said, oh, it's undefined, and then we would have been done with it, right? But what the limit allows us to say is we can find what's happening around x equals 0. We can say that, well, the limit as x approaches 0 of that function is equal to 1, and so we can get a better idea of what's going around that value, even though we couldn't plug it into the function and get a value. And another reason is that they're really essential to defining what's called a derivative, and derivatives and integrals are like the two main reasons why people truly study calculus. Very applicable for sciences, engineering, and other sorts of things. Okay, so we actually, without you guys realizing it, we did introduce this idea of what's called the left-handed limit and the right-handed limit. Okay, and so what this is here is, below you can see that I have the left-handed limit, and we say it's the limit as x approaches a number c from the left of f of x. So this is our notation for that. You can notice this little dash above here. This means to the left. Okay, and then similarly for right-handed, we say the limit as x approaches c from the right of f of x, and we use this notation here. That little plus sign means to the right. Okay, and why am I saying we already talked about this? Well, when we go back to the first page and we looked at these two separate tables, this part up here would represent x approaching 0 from the left, because we were looking at x values that were to the left of 0, and we were getting closer and closer, right, as we were traveling from the left of 0. And same thing for up here, this would represent x as it approaches 0 from the right, because we were looking at values to the right of 0 that were really, really close to 0. Okay, so that's basically why I said we kind of already, without you guys realizing it, defined these two things. Okay. So now let's look at an example here. So use the graph below to compute the following one-sided limits. Okay, so I have this beautiful graph of this function f of x, and the first part is asking me to find the limit as x approaches -1 from the left of my function f of x. Okay, so let's first find the x value, -1. So here's -1. Okay, and this part here is telling me to the left. Okay, so all that means is now I want to look at values that are to the left of -1 on the number line here. So I'm going to be looking at like these types of values that I highlighted in purple. Okay, and now I want to look at these points on here, and what you can see is as I keep drawing these purple points, what output value or y value am I getting really, really close to? Okay, so as I was drawing those purple points, okay, I was drawing them, what y value does it look like I'm getting very, very close to? Because of course I'm getting very, very close to the x value of -1, but it looks like the y value that I'm getting very, very close to is 2. Okay, and so we would say that this limit here is 2. Okay, let's try to look at the limit as x approaches -1 from the right. So again, just to remind you, this means to the right. Okay, so now instead I'm going to use pink, and I'm going to highlight some values here that are to the right of -1 on the number line. And now I'm going to look for these points, okay, correspondingly. So as I draw these pink dots, as I get very, very close to -1, what output value does it look like these points are approaching? In other words, what y value does it look like these points are approaching? So you want to be looking at the y-axis now. And so hopefully, if you see me draw these things again, just sort of emphasize them again, what output value or y value does it look like I'm approaching? And so hopefully you say that it looks like I'm approaching 4. Okay, at this point here I would try to pause the video and see if you can do part B. Okay, now let's try to do the limit as x approaches 1 from the left. So I'm going to use a different color. Let's use red this time. Okay, so I want to be looking at values, x values that are to the left of 1. So I'm going to pick these 4 values here. And now to find the limit as x approaches 1 from the left of f of x, I'm looking for the output value I'm going to be approaching. So I'm going to plot these points. And so what y value or output value am I approaching as I'm moving closer and closer to 1 from the left? And so as you can see, when I started plotting these points, I'm going to re-emphasize them again. Hopefully you see that the y value I'm approaching there is 2. Okay, Now let's try to find the limit as x approaches 1 from the right. So I'm just going to pick some values here. And so as I'm coming towards 1 from the right, what output value or y value am I getting really, really close to? And hopefully you see that this is 2. Okay, so I know this is really, really tricky. Okay, so if you're not understanding what's happening in this video, no worries. You do need to tell me though, so I can try to explain this to you differently. All right, this is really, really tricky. So please do let me know if you do not understand what's happening in this video. Okay. So now the last thing I want to do before I just conclude these notes is let you in on something important here. So if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x, which is equal to L, okay, so some number, where L is finite, in other words, it's a number, then we say the limit exists and the limit is equal to L. So what I'm saying to you basically is if the left-handed limit is equal to the right-handed limit and they're both numbers, that means the limit overall of that value is equal to that number. So in example 2, we see that the limit as x approaches 1 of f of x exists, and the limit as x approaches 1 of f of x is equal to 2. Okay, this is because C in part B, how the left-handed limit is equal to the right-handed limit, which is equal to 2. So then that means that we have that the limit as x approaches 1 of f of x is equal to 2. So that's what this important fact here is saying.